Hello everyone, I'm Parthiv. Welcome to the session where we are going to teach navigation. So we split this video into three parts. First part is going to be about basics of navigation, and second part is going to be about path planning and algorithms, and third part is about SLAM and visual localizations. So we have covered this in three parts. So let's get started with the video. So basically, in this session, we are going to dive deep into basics of navigations and how and the simple path planning algorithms like left follow robot. So let's get into navigation. So have you ever wondered like how a self-driving car stays in its lane, or how a drone flies through a dense forest without crashing? Like these systems, like they aren't magic. They're just result of like advanced navigation algorithms basically. So what like we can so after like analyzing all the navigation, like there are four main pillars of navigation, like how do we control and how we actually make the robot think and move in a way. Or we can say the four questions is basically the questions given here. Like the first one, where they are, localization basically. We'll get into that in more depth, like in just a minute. And what's around them, perception, like what do they see? And the third question, where they need to go, what is their aim, where to go, and how to get there safely. Like what is the path planning to do that, and like in reality, what is going on. So let's get into what these are and what these are not. So getting into next slide, there are four pillars of navigation as we discussed earlier. So first point is about perception. Like robot use sensors like lidar and cameras, ultrasonic sensors and sensors to sense the world around them basically, and how each section is there. And the second is localization. Localization is like finding where itself it is on the map, like knowing where it is. So for a robo in navigation, importantly, a robo needs to know where it is. So it is done by localization. That algorithm of where it is, it done by localization. The third one comes to path planning. So basically, in path planning, what it does is it basically selects a target location and it plans a layout of how to go there. What are the speeds of the motor I have to put? Like ideally, what are the speeds of the motor I have to put to go to there? What is the speed of the propeller in a drone, for example? What is the speed of a propeller for a drone so that it goes from one place to other? So it basically plans the path of what it should have. And the fourth point comes to control. What control does is basically it implements the path planning algorithms. Sometimes due to errors, the motor may not rotate in the desired RPM. So what control does that is it tries to adjust that error by changing the voltage of the motor or changing the speed of the motor. That's what control basically is, a mind of execution, we could say. So now getting more in details with perception. So let's get into a few sensors. One is these are like major sensors. Like one is lidar, which scans the entire room, and the second one is cameras, obviously, which I'm also recording with, and ultrasonic sensors, which we use, which bats actually use more. Like they use the echo in the cave and to detect how far an object is. Their sight is very weak compared to a human. So, and then IMUs are like measured. They measure how much is the tilt, or like the acceleration of the thing, or like the RPM of the motors, or the acceleration of effective acceleration of the robot. Like IMUs, we can say they are like the middle part of the ears, basically. That part where we sense because of balance, like how is the orientation of my head, like is it in this way so that the ball moves in this way. So basically that kind of thing is an IMU. It basically tells the orientation of the robot which is currently it is. Like I want to go deeper into lidar because lidar is different from ultrasonic sensor in many ways. Like lidar basically is a laser. It's like a cane for a blind man. He taps around like where is this portion and where is that, where is this. So in that way, it he gains the knowledge of the surroundings basically. So basically, lidar is better version of ultrasonic sensor, we can say, but it is a bit costly because we are using lasers, and in ultrasonic sensor we are basically using sound in the same way basically. the sound it propagates slower, so it has a higher range, higher clarity in lower range rather than uh, lower distances. But in higher distances, it is not as effective because sound gets distorted a lot by around all the surroundings. But light doesn't get distorted by the surroundings, except there are does not get as distorted as sound. So it's much better to use a lidar sensor if we are aiming at a larger area, and we have a lot more budget than ultrasonic sensors. So that is a basic difference of lidars and ultrasonic sensors, because I got confused when I was doing my tenure, like what is the difference. So I just wanted to put it out there and clarify. So getting into next part, which is localization. So coming to localization, like what is actually localization? Like localization is detecting itself where it is. Like us knowing if we are on Google Maps, like what do? We check for names in Google Maps. Like if we are lost in somewhere and we have our phone and we just open the Google Maps, and for some reason our phone's location is not working. So what do? We check for nearby things, like what is for example, there is some XYZ Kirana shop there, and ABC Baba Saloon there. You yourself know that I'm exactly opposite of this, and this is I am on the road, and I am at a 45 degrees angle from this. So well, I must be in this point. So from there you will know where you have to go. How to You look at the map, and you know, after going, and according to the map it says that after going 2 meters turn left to reach a bus stop maybe. So in that way, when even a robot detects itself where it is and then continues ahead with path planning. So there are multiple techniques for path planning. There are multiple techniques for localization. One is GPS, and the other is like tracking it where it is like odometric. As I said, using those IMU sensors where its velocity, and from previous location, it basically tracks how much it went forward and remembers that thing. And then there is SLAM, which will get more, which will go dive deep in the third lecture. So, uh, so there are also actually like many challenges in sensor noises. Like there might be some errors in sensors, and that is what causes a lot of issue. So that is how we need to minimize the error, and all we need to look for ways which minimizes the error. And second point is dynamic objects, which means moving objects, and also uh, to compute a lot of data. I mean, if we increase the number of sensors and process a lot of data, we also need a lot of processing power, which may also be a problem and need a lot of optimization. And fourth point is cumulative errors. Like these small errors, even if you think they are small, but over a lot of time, when the robot moves, the errors stack up on each other, and they may lead to a higher and a high amount of error. So these problems will be covered by these problems will be mostly solved by good path planning and good control overall. So let's take an example of a robot. So a robot tries to make a certain of landmarks. Like let's just take a robot in middle of nowhere, and let's say 4 points A, B, C, D. These are marked as landmarks for the robot. Now what happens is calculates the distance from each of the point and remembers the location. Now it moves forward. Now after moving forward, you can see that A, D are similar and B, C are similar. So that means the robot must have moved in the forward direction by basic mathematics. And you can see AD has increased and BD, BC have been decreased. So from this, it moves from the basic location, move forward. Now let's just take few circles around these points, and let's just put the robo aside. We don't know according to the robo, it doesn't know where it is exactly. So now let's get into a bit of way of how a robo can calculate this. Now let's just take a circle as center on these points, and with radius being its length from the robo to B plus error plus a buffer we are adding, so that there will be intersection of all these 4 points. Now let's just take the intersection of all these four circles. Well, you can see this is the area of probability where the robo can lie. Now, this is a quite big area. Let's add another sensor the robo has previously calculated. Now let's look at the intersection data. Well, it has decreased. Now, as it decreased, that means we have smaller area of where the robo can be. This increasing a sensor technically increase the precision also. So having more sensor leads to more and more accuracy. So in this example, if we look at the example of dynamic robo, what happens is like if, for example, the object set a landmark on a dynamic object, like for example a cat, for example. So what happens here is the distance is changing. So now what it should do, it gets confused. So we need to also build a system which also accounts the fact of this dynamic objects, and it detects that yes, this sensor reading or this data which I'm getting is very different from all the three data. So this must be a dynamic object and treat it as a dynamic, or basically neglect that certain information from that sensor for now. Or it might be from a faulty sensor. Basically, suddenly the robot might think for the sensor might have a fault or something. So this detection should also be into account fed into localization basically. So we need to know how a robot actually works. That's it for localization. Now let's go moving into path planning. Path planning basically, as the name says, planning the path to the destination. Basically. So for this, there are multiple algorithms and what we consider. Like these algorithms depend on what we are looking for. So there are algorithms like A star, digital star, and RRT, and flat fill, which we will cover in deep in next sessions. Next session. So in this session, we'll be covering about left follow robo and bug algorithms. So let's get into like how left follow robot works. So let's take what does left follow robo mean? Basically, it sticks itself to the left side of the wall. So it tries to maintain a distance from the left wall and follows the left wall continuously. Let's, for example, try this maze. So here's the maze. We are trying to solve it with right follow robo instead of left follow robo because I feel right follow robo is more suited for this thing. So basically in right follow robo, we have priority of first moving right, then moving forward, then moving left. So the priority is as follows. So now the robo moves straight as right part is occupied because that is the only way it can go. Now it reaches the dead point where move forward is not available and this is not available. So it turns right then moves forward. So just want to clear out a small thing here. Movement for both of the bots are different because this is a headless bot and this is a headed bot. So for a headless bot, moving right is just turning directly moving right. But for a headed bot, it has to turn right then move forward if the path ahead of it exists. So let's just get back to the maze and let's see how the robot runs. Now it moves right because right is available. Same again. After moving forward, it has right is not available, so it turns left, and as forward is also not available. Right is available, so it turns right and moves forward. Turns right, checks if forward is available, then moves forward. Turns right again. Now let's see what happens as we approach a dead end. So here it takes two left turns. That is because I have coded it so that when it senses an object in all three sides, I coded it so that it makes a left turn. Now it again detects a left turn because right is unavailable, so it makes another left turn. So in that way, it makes a complete U-turn. In the next loop, I just made it so that it completes a U-turn basically. It turns around here, complete U-turn. In reality, it just turns two times right. Now the program just speeds up. I just want to mention another point here that in right follow robot, priority is right. In left follow robot, priority is given to left first, then moving forward, then moving right. So yeah, both those are basically the both following robots. Basically, evolved following robot is what we can say. So it basically went into three dead ends, as we see. Now that it is approaching the end, let's see how it goes. Now we can see here that the robot actually just went and touched this red line wall, and it, even if the black line wall is absent, it doesn't matter. So now let's see what happens if there is the exit point is on the other side, which is not in contact with the orange wall. Well, if you see, it doesn't go to that exit, rather it continues to stick to that red path wall, because the exit is not connected to the red path wall. So this is one of the limitations of the right or left follow robot. Let's get into the next algorithm, bug algorithm. What is this? Is basically it draws a straight line from path to its starting position. It needs some amount of map knowledge basically. Now what it does is when it faces the faces an obstacle, it goes around it and goes to the location. See a simulation of bug algorithm. What is bug? Let's say there's a bug and there's a flower. It wants to go to there. So what is the path? Straight. It just saw that it wants to go there. And it knows the direction of that, so it just travels in that direction. No, what if? What if there is a stone in the middle? Well, what does the bug do? It goes around the object. That's it. That's a bug algorithm for you. Actually, the robot just needs to know what is the direction of the location and it just tries to go. Well, the bug algorithm also has its disadvantages of itself, like it may not be as quick as uh, other optimized algorithms, but it is the simplest algorithm which doesn't include any mazes or sorts. This is literally the simplest algorithm, like the two simplest algorithms. The bug algorithm, there are quite modifications of it, and left follower also there are a lot many modifications of what to do. Like if there is a loop, like they add a condition. If you got to the same point three times or more, then you need to change, go right to explore more paths. Basically, uh, there are versions of left follower which will not get stuck, but they are not as optimized as other planning algorithms like A star, Digital and RRT. So each has its own use. Like left follow robo is like just so simple to implement, and it can be solved. Like 90% of mazes it can be solved. Like there are mazes we can make which cannot be solved by left follower or bug algorithm. Bug algorithm is very bad at solving mazes, but it is very good in like what do we say, a vacuum cleaner for example. In algorithms such as vacuum cleaner where there is a lot more open space, bug algorithm wins over uh, left follow robo. But as I said, it depends on the situation of what algorithm and what is the condition. Like for a algorithm it's better in this way. That's it about path planning. We'll get more into path planning in the next session, to be honest. Like these are like just basics of Graph Solver. I would actually suggest a website called Blockly Games. This is, you can consider it as an assignment. So this is basically the game. It's like a game. You basically have to play these games where there is like certain number of games. One is maze, which at the end they'll build you up to the point of left follow row, how basically the code works, and this gives you the basic navigation beginnings, like how do we actually move towards navigation basics, like how are different algorithms. Like in the end, the pond is like the final boss, you could say, which actually has like three different bots which have different algorithms of shooting you, but you have to basically shoot them back with their basic code. So it just builds you through that process, and try out. The puzzle is the easiest one. I would rather skip it. It's nothing much, but if you want, you can complete the blocking games. So this is your assignment for until the next session. Just be good with it. Just complete it. It is gonna take like 2 days, I guess. Not even 2 days. Like I completed this. It's gonna take max 2 to 3 days. It's your choice. Like okay, getting back. So basically, what is control? Like the implementation of the plan we pre-planned during the path planning process. The execution of that comes into this. So in path planning also there are two types of path planning. In control also there are two types of controlling. So one is open loop and the other is closed loop. So what is open loop? It executes without feedbacks. It like as we said in left follow robo, it just executes. It goes. Okay, there's there. Okay, that is there. Okay, that's it. It just executes what is there. Open loops, which mostly control of uh, it just says once it just says the controllers like what to do, and they just follow that mark. This is good, like it's very cheap for processing cost as well, and done, it gets the job done basically for a specific means. For example, I want to just solve this specific means. I just remember turn left, turn right, turn left, turn left, turn left, turn right, and it just reaches this location. This is what we call open loops. Like, okay, turn left, turn right, turn left, turn right, turn left, and do it until we get to the destination. So it does that. We don't need to do anything. It's like just an open loop. In closed loop, it always checks its surroundings of what is going on what sensors are the values reading. So it is more good and adjusts the value of those adjust the values of the and changes the path plan basically. So it takes the input and again gives another input. So this is what we call a closed loop. So basically it reads the data, sends the data, reads the data, sends the data in the same way and goes in a loop basically. In control, there is PID, which was covered by Krish in the previous videos. In his videos, the link will be in the description. Uh, Very basically, what it does is it tries to set the value and minimize the error basically after getting a lot of error, and it tries to minimize the error basically. It's like easiest way to implement. There are other algorithms which use certain types of PI controllers as well, which are not PID but specific to that robot, specific to that robot and how it operates. Some might need a bit of more specialization in PID, or some might need an entirely different way to uh, control a motor or a car, basically. So that all those controlling part comes under the control section of this. Now, getting back to the types of navigation, basically these are like this is the types of navigation based on like the reactiveness. So there we can say it's not like two types; it's like a gradient. So I would say this is more of a gradient than two types. So one is the reactive navigation and the other part is deliberative navigation. So what is reactive navigation? Is Reactive navigation is not, there will not be a lot of path planning, there is more of control. And in deliberative navigation, there is more of path planning than there is control. Uh, it's like a slider basically. So if you put in reactive navigation, like best example is left follow robo, it just follows a set of rules. Reactive navigation, okay, there is a left path, so just follow the left path. There is minimal path plan. There is minimal path planning in this. There is mostly control in this. Uh, and then in deliberative navigation, it's more of path planning on how to do this from this to this. Okay, these are all the possible combinations which I can go. So I would choose the best optimal one. This is the best optimal one. Okay, but this might be not good enough because the processing power, and for sudden changes, like suddenly what if while solving a maze or while cleaning the room, a cat appears in the room. For sudden changes, we need some reactive navigation, and for optimized changes, we need deliberative navigation. So you can put the slider anywhere in the middle if you want more reactive response, and you just want the job done and be as reactive as possible and be ready for any situation. You can go with reactive navigation, put the slider on the reactive side, and if you want more of the optimized path and be less ready for the reactiveness, but also be as reactive also be reactive so that the robo cannot be disturbed, you can go put the slider on this side as well. Getting back to challenges in navigation and why do we need navigation? why do we need navigation? Like, as we discussed all these points, like they help us in doing this segregation and this way of making it a separate way. We can do a lot of stuff like flying airplanes in autonomously, like Tesla car is there, for example. These are all autonomously built. They don't need a human intervening in between them most of the time. Okay, coming to challenges in navigation of basic robotics, the main challenges are partially like how do we actually know the environment? Like how do we record the environment? How to remember the environment? That solution is solved by that can be solved by good what to call localization and perception. And the second point, as I said, is dynamic obstacles. These are like then comes sensor limitations uh, and of budget optimizations. These might be vary a lot, and nowadays like the sensors errors, we need to minimize the sensor errors as we discussed earlier. I just mentioned a method of how can try to reduce the error by increasing the number of sensors, but also it increases the budget. Like also in localization, I want to mention a point. Like if, for example, we just put a robot in uh, unknown map, for example, what happens is it cannot do path planning because it doesn't have the required map. It cannot do okay. It tries to localize them, but it cannot move because it doesn't have path planning. So basically, it's basically like chicken and egg, which came first. So we need to solve it by doing both at first, both at some same time, like simultaneous localization and mapping, which is called SLAM, which we'll get more into in third session. So basically, what SLAM does is it while localizing, while knowing where it is, it also tries to map its surroundings. We'll get more in detail with this in the next lecture. So till then, you can just do the assignment, which I gave you the broccoli games. And that's it for this lecture. So let's get a quick recap of what we did. Like we got to know like what are the four pillars of navigation, and they are perception, localization, path planning, and control. And how do they affect each other, and how do they help each other in making the robot move from one place to other. So in the next session, we'll, as I said before, in the next session we'll dive deeper into path planning and algorithms, path planning path planning algorithms, and uh, till then, please try to complete the assignment which I gave. Yeah. And that's it for now.